Section 3.7 is indeterminate forms and L'Hopital's rule. So this is another way to evaluate limits. It's a very important tool, and it's particularly useful. Well, it's really only applicable when we can get our limit function, or the function we're taking the limit of, into some sort of indeterminate quotient. All right, so if we look at the example I have below, we realize that taking the limit as x goes to infinity, this is natural log of x over x minus 1. As x goes to infinity, the natural log of x goes to infinity, right? So we see this here. And as x goes to infinity, x minus 1 also goes to infinity. So oftentimes when we've seen rational expressions, they were actually rational functions. We had easier tools, or those are just easier examples to actually evaluate what the limit is overall. But we've seen limits that look like infinity over infinity. You know, this character out here, this intuition that I've quoted. But we've seen that they either converge, diverged, or converge to a non-zero number, or converge to 0, or diverge to infinity. So we'll have similar cases now, but we don't really have any obvious algebraic tricks we can use on this function as we see it. So we have to start to think about what we might be able to do to tackle a ratio like this, right, in terms of its limit. Well, it turns out that L'Hopital's rule gives us a really nice tool for that. So we have f and g are differentiable functions. G prime of x is non-zero near a, except possibly at a. So, right, we're playing that same old limit game. Everywhere around a except possibly at a, right? So we don't worry about what happens exactly at a. Okay, suppose that both limit as x approaches a of f of x is 0, and the same for g of x. It's also 0. Well, what we'd have if we had f of x over g of x, right? The limit of this ratio, we'd have 0 over 0. And this would give us this indeterminate case. We're not sure what this is going to come out to, right? Any of these quotations that I put here, I'm never going to try to do algebra with this. I'm just marking off to the side more for the student's sake, as the person providing this material, just to get an intuitive feel for what's going on and to know what I need to do next. Now, as a student, if you're being graded on work, I suggest you use this notation just to kind of suggest what you've assessed so far. It's not really actually part of the mathematics. That's why I put it in quotes. Similarly, if we had the other case where the limit as x approaches a of f of x is equal to infinity, and the same for g of x, and it'll turn out that it doesn't matter if either one of these is positive or negative infinity. We'll have some infinitely large number over some other infinitely large number, positive or negative, it won't matter. We'll have this other indeterminate form. So if we have either of these cases for a ratio f of x over g of x, then what we can do, and this doesn't seem like it's very helpful at first, but we'll see this in use in just a moment, the limit of this ratio of functions is equal to the limit of the derivative of the top function over the derivative of the denominator function. This is not the quotient rule. Right? We're evaluating a limit, and we're using this interesting formula, this L'Hopital's rule, or essentially a theorem here, in order to change the limit we're trying to evaluate that we're not able to directly evaluate into something that might actually be directly evaluated. Okay, and this is only true if the limit on the right side exists or is not infinity or negative infinity. Okay, so we can't really make any conclusions about whether or not it diverges based on this. So let's have a look at how this thing works out. It turns out this actually goes a long ways for us. It even handles rational functions, as we've already been able to do algebraically. So to get to that initial function I used as an example to start the talk, we're going to look at this limit. Now, I remember that we pointed out that this was infinity over infinity. So we have that indeterminate form. This is a quotient, right? And of course, this is the direction that we think of this, right? What we're ultimately thinking about is I have the limit of a ratio of two functions, and then I split it apart and see what each of these numerator and denominator limits are approaching. And if they match as 0 and 0 or infinity and infinity, well, then I can apply L'Hopital's rule and hope that something easier to evaluate comes out or something that does evaluate. So since this is the case, I'll write down my limit, and I can use L'Hopital's rule to say that it's equal to this limit. And look what happens with this limit. I'm taking the same limit as x goes to infinity, but of the derivative of natural log of x divided by the derivative of x minus 1. Again, that's not the quotient rule. It's what we wish the quotient rule was, and the quotient rule is not that either. So just keep that in mind. This is just a direct derivative of the numerator and a direct derivative of the denominator. Well, the derivative of natural log of x is 1 over x. The derivative of x minus 1 is just 1 minus 0, potentially, or just 1. So we're taking the limit as x approaches infinity of 1 over x over 1. Well, that's just the limit as x approaches infinity of 1 over x. And of course, that's 0. Remember, that's our reciprocal function, and it has a vertical or horizontal asymptote at 0. So as x goes to infinity, 1 over x goes to 0. Okay. So that's nice, because here we really didn't know what this thing was going to go to, right? If we tried to evaluate it and consider it, all we could see is this intuition. We don't have an answer, right? But it turned out in this case to go to 0. What that really means, for some depth to this, it means that x minus 1, at least as x grows to infinity, x minus 1 grows faster than natural log of x, right? If it's able to drive the whole expression to 0, it means that x minus 1 is a faster growing function than natural log of x. So it's an interesting point, particularly for those who are concerned with computational complexity and perhaps a computer science course. So down here in our second example, we're going to look at the limit as x goes to infinity of x squared over e to the x. And same thing, x is going to infinity, so x squared is going to infinity. E to the x, an exponential function, is also going to infinity. We have an indeterminate form of infinity over infinity. It's appropriate to use L'Hopital's rule now. And this is what we'll see with that. Here's the limit of our function. And by L'Hopital's rule, this limit is equal to this limit, where we take the derivative of x squared to get 2x, and the derivative of e to the x to get e to the x. And now we assess again. I look at this limit and realize as x goes to infinity, the numerator goes to infinity. The denominator also goes to infinity. I still have an indeterminate form, infinity over infinity. I can use L'Hopital's rule again. So I do that. The limit as x goes to infinity of the derivative of 2x is 2, over the derivative of e to the x, which is e to the x. And now I see, well, I can factor a 2 out if I like. That'll just be a 1 right there. Here's a 2. And I did this sort of a strange way maybe, but we can look here and realize as x goes to infinity, this thing is driven to 0. E to the x gets really large. Nonetheless, here's this other way of doing it. Factor a 2 out, and then 1 to the x is just 1, which is the one that would be here times 2, over e. This is gives us an e to the x. 1 over e is less than 1. So 1 over e to the x goes to 0 as x goes to infinity. So however you want to see that, right, e to the negative x goes to 0 as x goes to infinity. We get 0. Again, I think we're fine right here just to say e to the x goes to infinity, 2 is holding still. Overall, this thing goes to 0. Okay, our third example. Find the limit as theta goes to pi over 2 of 1 minus sine theta over 1 plus cosine 2 theta. So a little bit more tricky. So what's going on in the numerator? I could plug in pi over 2. Sine of pi over 2 is 1. So I have a 0 in my numerator. 1 plus cosine of 2 times pi over 2. That's cosine of pi. Cosine of pi is negative 1. So 1 plus negative 1 is 0. So I have 0 over 0 as my behavior here. That's an indeterminate form. I can use L'Hopital's directly on this. So this limit is equal to the limit as theta approaches pi over 2. Same limit information, right? But the function now, I can take the derivative of the numerator. The derivative of 1 minus sine theta is negative cosine theta. The 1 is a 0, and negative sine theta's derivative is negative cosine theta. The denominator takes a little bit more work. Derivative of 1 is 0. And this is going to be negative sine 2 theta is the outer derivative times the derivative with respect to theta of the inner function 2 theta gives us that multiple of 2 right there. And now we assess what we're looking at here. So the negatives cancel, and the 2 will factor out, or the 2 in the denominator will factor out as a 1/2. We'll check to see what these functions are up to now. As theta approaches pi over 2, cosine pi over 2 is 0. Sine of 2 times pi over 2 is sine of pi. Sine of pi is 0. Again, we have 0 over 0. It's another indeterminate form. It's perfectly feasible to use L'Hopital's rule again on this. So this is equal to same limit, same constant. We take the derivative of the numerator, which is negative sine theta, over the derivative of the denominator, which is cosine 2 theta times that chain rule constant of 2 that comes out from the derivative of 2 theta. So now I've got negative sine theta over 2 cosine 2 theta in my limit, and I'm curious about what happens to this. Well, I have a negative 1/2 I can factor out and multiply by 1/2. So this becomes a negative 1/4. And then I'm taking the limit as theta goes to pi over 2 of sine theta over cosine 2 theta. Well, sine of pi over 2 is 1. Cosine of 2 times pi over 2 is cosine of pi. Cosine pi is negative 1. I have 1 over negative 1 in here. And then that negative 1/4 as a multiple out front. So I have positive 1/4 is my overall value here. So this thing evaluates to 1/4. Now, leading up to this, it was maybe not interesting. We started to think, well, maybe everything will converge to 0. Interestingly enough, and thanks to L'Hopital's rule largely, that's not necessarily the case. We could see that right here. Now, perhaps there's a way around this. I think L'Hopital's rule is the nicest way to solve this problem. But perhaps you could use a double angle identity and get really tricky with some trig identities and do this without L'Hopital's. But that requires a lot of sort of fleet of foot mathematics and some quick thinking. This really doesn't require that. You just have to keep checking that you have an indeterminate form and then applying L'Hopital's rule so long as you do, until you can evaluate that limit. Okay, so another indeterminate form we might come across as an indeterminate product. And this is, I put it in quotes, the case where we have something like infinity times 0, or something that looks like this in our intuitive assessment of the problem. Okay, so let's have a quick look. There's a trick to these. It's not very difficult, but we'll see this in just a moment. So the limit as x approaches 0 of x times natural log of x. Well, this number approaches 0, so we get a 0 here. This function approaches, well, negative infinity, right? And it doesn't matter that it's negative, it's 0 times something infinite, and that's suitable enough. So 0 times an infinite value is an indeterminate product. What we need to do is pick one of these functions to write as its own reciprocal. In other words, 1 over that function, 1 over x, or 1 over natural log of x, and write that into a denominator here. So what we've done in this case is we've left x in the numerator, and we've written natural log x to the negative 1 in the denominator. Of course, if I simplify this expression here, I'll get back my original expression over here, right? We could see that quickly. Move natural log of x back into the numerator, and it'll be natural log of x without a negative 1 power anymore. Now be careful. I cannot use the third log law on this. It has to be the argument x to the negative 1 in here, not the whole natural log function to the negative 1. So don't make a mistake like that. Now, once I convert this into a quotient form, I can check to see whether or not I have a proper indeterminate form for L'Hopital's rule. And I'll do that. Looks like my numerator, as x goes to 0, well, the numerator goes to 0. My denominator is 1 over natural log of x. Well, natural log of x goes to infinity as x goes to 0. So 1 over something going to infinity is going to 0. Right? So there we are. I do have an indeterminate form. I have 0 over 0. Okay, So now I can use L'Hopital's rule to take the derivative of the numerator, put it over the derivative of the denominator, and take the limit of all of that. See if I can evaluate that at this point. So this thing gives me 1 in my numerator as a derivative. That was easy. And then chain rule, -1 comes down, times natural log of x to the -2. This is the power rule for derivatives. And then times the derivative of my inner function. My inner function is natural log x, so that its derivative is 1 over x. Okay, and this starts to look a little messy, but I can take this 1 over x, and it's x to the -1. I can push it into the numerator here as just an x, right? Just check that on your own if you like. And I can factor the minus sign from this -1 out front. And what I end up with is an expression that looks like this: x over natural log x to the -2. And maybe it takes another round of this for you to convince yourself that this is probably a dead-end method, right? If I do it again, I'm going to have a negative natural log, or -2 natural log to the -3, and then times a 1 over x. This is going to be a 1 up here. That 1 over x comes back up, and I have another x in the numerator with a natural log x to the -3, and I never really get anywhere. This is going to 0. This is going to 0 as x goes to 0. So I still have an indeterminate form, and that's never going to go away. Luckily, I can try the other direction. I didn't need to force natural log of x into the denominator. I could force x into the denominator and leave natural log of x in the numerator. So if I push x into the denominator, it's going to be x to the -1. Natural log of x will be itself in the numerator. If we look down here, this is us retiring to another method, right, or resorting to another method. So try another way. Here's our original problem. So I'll push x to the -1 down here. Well, now as x goes to 0, natural log of x is going to -infinity, or just infinity, or an infinite value. X to the -1 as x goes to 0 is also going to infinity. I have infinity over infinity. I can perform L'Hopital's rule on this function to see if its limit is easily evaluated in the next step. The derivative of natural log of x, or the numerator here, is 1 over x. The derivative of x to the -1 is -x to the -2. Now I start to simplify. This is looking a little bit better than it did before. All these functions seem to be related to one another. So negative, that came from this minus sign here, but x to the -1 is 1 over x, and we have an x to the -2 in the denominator. So this simplifies with this minus sign in front to 1 over x to the -1, or I can think about it this way. I flip these two. This becomes x to the 1 in the denominator. This becomes an x squared in the numerator. So this is just x squared over x. And again, the minus sign's along for the ride. X squared over x is just x. This is negative limit as x approaches 0 of x. Well, x approaches 0, so this limit approaches 0. And there we are. That way worked. So it could be that both ways might work, right? Using L'Hopital's rule. So one way might be easier than the other, or more direct. I believe this was the easier one to see. I don't know really where this process leads without getting more clever than just using L'Hopital's rule. So be sure to try one way or the other when you're dealing with these problems. Okay, the limit as x approaches infinity of x times tangent of 1 over x. Now it's getting a little more interesting. As x goes to infinity, this function x goes towards infinity. As x goes towards infinity, 1 over x goes to 0, and tangent of 1 over x, or tangent of 0, goes to 0, or is 0. Okay, so tangent of 1 over x approaches 0 as x approaches infinity. So infinity times 0 is my indeterminate product. I cannot do L'Hopital's rule on an indeterminate product. Can't do that. I have to write this as a quotient in order for it to be valid. And in order to do that, I think the easiest thing to do is to take this x, write it as 1 over x, or x to the -1, and place it in the denominator. Right? Again, because if I simplify this expression, I get back my original expression here. You just need to transform it into a rational expression like this, or a ratio, or a quotient, something with a division bar, so that you can get a form, an indeterminate form or an indeterminate quotient, to use L'Hopital's rule. Now we check. As x goes to infinity, 1 over x, or x inverse, still goes to 0. Tangent 0 is 0. Denominator, as x goes to infinity, x to the negative 1 goes to 0. So we have the indeterminate form 0 over 0. We're ready to take the derivative of the numerator over the derivative of the denominator and try to evaluate that limit as x goes to infinity. So derivative of tangent of x inverse, our outer function's tangent, its derivative is secant squared of whatever its argument is. Now, times the derivative of its argument. Well, its argument is x to the negative 1. It has a derivative of negative x to the negative 2. Right? The negative 1 comes down from the power rule, and we subtract 1 from it to get negative 2. And the denominator, same. Negative x to the negative 2 is our derivative. Interestingly enough, there's a factor of each of these in the numerator and denominator, and we see that they've been canceled in this work already. So they're out. We're taking the limit as x approaches infinity of secant squared of x inverse. Well, what happens here? As x goes to infinity, x inverse goes to 0. Secant squared of 0, well, we need to be able to evaluate that, but it turns out that that's going to be 1. So if you want to check this, you just have to remember how to evaluate, and this is a good thing to work on. If you don't know this, then you certainly want to be sure to understand why this is what it is, right? So I'll put a little question, why or how, right? Rehearse some trig there to remember why that's the case. Remember, secant is 1 over cosine. That's your hint. Okay, so those are indeterminate products. It gets worse. Indeterminate differences. This is an infinity minus infinity. Now, this won't be the case with 0 minus 0. 0 minus 0 is simply 0. So that's fine. But we cannot do algebra with infinity, right? So if we come out to intuition that looks like this, we got to be careful, right? I'm not sure why I have an over infinity here. Maybe I'll strike that because I really don't like the look of that, right? We don't know what this comes out to, right? This is not a real number minus a real number. Infinities are not created equally, right? When they show up in calculus, they're not, of equal magnitude. One of these functions may be faster than the other one. So let's see. So typically with this, we'll either do some kind of algebraic simplification. If these are rational functions, we'll combine them, right, with a common denominator. That will often fix an infinite difference, right? So, or an indeterminate difference. If we have a polynomial function and a logarithmic function, well, we want to be a little bit more clever about this. We can probably combine these. We just have to remember properties of logarithms. So this limit, as x goes to infinity, of course, as x goes to infinity, this is going to infinity, and natural log x is going to infinity, and it's approaching infinity minus infinity, which is indeterminate. We don't know what that is until we do more analysis. So what I'll do, I want to introduce another logarithm, and we'll see why I do that in a couple steps here. So I can write x as natural log e to the x from our cancellation equation. Now I have log ln of e to the x minus log ln of x. That's good, because the difference of two logs I can write as the log of the ratio of a over b, or e to the x over x, right? So remember, that's the second quotient log law, or that's the second log law, the quotient log law. So usually we see it written and we think of it in this direction. If I have the log of something over something, I can split it as the log of the numerator minus the log of the denominator. I can go the other direction, and it turns out that that's useful for me. So that's what we do here. Now I look at this, I realize x is going to infinity, so this is going to infinity, and this is going to infinity. So I kind of have an indeterminate difference, or a quotient, right? But what I have to know now is that logarithm is continuous. So continuous functions allow the limit to pass inside their argument and be applied to their argument, right? So log allows limit to pass inside and apply to the function in its argument. And then we'll just take the log of the result. Okay, so what happens here then? Well, the limit, or log, it's log of the limit as x approaches infinity of e to the x over x. This is approaching infinity. This is approaching infinity. Okay, so what we can do is take the derivative of the numerator, place that here, the derivative of the denominator, place that there, applying L'Hopital's rule in this step, and we have e to the x over 1. Well, the limit as x approaches infinity of e to the x over 1 is, well, infinity. And natural log of something approaching infinity is also infinity. If we wanted to see this a little bit more easily, well, wonder if we could. Oh, we could reverse this property. We want to see one more step here. It might look nicer if we had this. We can reverse, because again, natural log is continuous, and this limit actually is going to exist, so this is fine to do. We take the limit of the log now. We can flip them around. Log is continuous, so it allows that passage of the limit. Natural log of e to the x is just x. And now we're just looking at this limit right here, which of course is infinity. And that matches what we had before. We don't have to do all those steps, but this fills in some of the details in case that wasn't clear. Now down below, we have another infinite difference, it looks like. X is going to approach 0 from the right. 1 over x, well, that's approaching infinity, minus 1 over e to the x minus 1. Okay, x is approaching 0. E to the 0 is 1. 1 minus 1 is 0. So the denominator here is approaching 0. 1 over 0, well, that's going to approach infinity. So I have infinity minus infinity. So I have an indeterminate difference. In this case, since I have two rational expressions, let's get a common denominator and see where that goes. If I have a single quotient, I'll probably end up with an indeterminate quotient. So here, e to the x minus 1 times this numerator and x times this numerator to get a common denominator of x times e to the x minus 1 leaves me with the following. This is this denominator times this numerator here. And then this denominator times this numerator is here with this minus sign. So there we have all those pieces put together. Now we assess where we're at. X is going to 0. This is going to 0. E to the 0 is 1 minus 1. 1 minus 1 is approaching 0, right? As x approaches 0. This is approaching 1. This is approaching 0. 1 minus 0 is 0 in the numerator. We have 0 over 0 as our indeterminate quotient now. We're ready to apply L'Hopital's rule in the next line, and we'll do so directly. It's the derivative of the numerator, which here is just e to the x minus 0 minus 1. So e to the x minus 1. The denominator takes a product rule, right? That's still applicable. The derivative of x is 1 times e to the x minus 1 plus x times the derivative of e to the x minus 1. Well, the derivative of e to the x minus 1 is e to the x, so x times that. Now we assess. Where are we? We've got, maybe we simplify a little first. Let's see if we can make this a little nicer. Well, we will look again. Let's see. It looks like I actually, just look at this. This is going to 0 again, right? E to the 0 is 1. So x approaching 0 drives the numerator to 1 minus 1, which is 0. The denominator is being driven to, well, this is driven to 0. This is driven to 1 minus 1 is 0. So 0 plus 0 in the denominator, we're being driven to 0 in the denominator as well. So we have another 0 over 0 L'Hopital or indeterminate quotient. So I'd take another derivative of this. Or I should take another derivative of this and use L'Hopital's again. The derivative of the numerator, well, that's just this e to the x. Derivative of negative 1 is 0. Then I have the derivative of e to the x minus 1. Well, that's just e to the x. And then plus the derivative of this function? Well, that's going to take a product rule. The derivative of x, which is 1 times e to the x, plus x times the derivative of e to the x is x e to the x. Now, I look at this. This is going to 1, this is going to 1, this is going to 1, and this is going to 0. I think things are working out now. I have 1 over 1 plus 1 plus 0. Looks like I have 1 over 2 overall. Right, but let me see. It looks, before I get there, it looks like I've combined some like terms. E to the x plus e to the x to get 2e to the x, and then plus x e to the x. Okay, now I can see that maybe more clearly. This is going to 1 over 2 plus 0 as x goes to 0. So my answer then is 1 over 2. Maybe an intermediate step here might be something along the lines of this is 1 over 2 plus 0 times 1. Right? Just to show a couple details. And of course, that leaves us here. So that's indeterminate differences. And lastly, and one of the most complicated cases are indeterminate exponents or indeterminate powers. Okay. So this is where we have a case, an indeterminate form that looks like 0 to the 0, or infinity to the 0, or 1 to the infinity. If we ever have anything that has an intuitive assessment of that, of one of these cases, then we have an indeterminate power or an indeterminate exponent, and we need to use essentially the method I'm about to outline below. So let's start with this problem. Find the limit of, as x approaches 0 from the right, of x to the power of x. Okay. You basically do this. Well, okay, let's assess it first. X is going to 0, so the base is 0. Then the exponent's x, and x is going to 0, so the exponent's 0. Our intuition is this thing is approaching 0 to the 0, right? That's our intuitive assessment. That's our indeterminate form, and it fits one of these. So we're now ready to use this method. This is not an exponential function, nor is it a power function. I can't use a power rule on it to take a derivative. It's just a hard thing to manage, right? So I have to be a little more clever about it. Remember, the tool that fixes exponential complication is the logarithm. So here's your step for this problem. You take the function in the limit and you call it y. Say y is equal to the function I want to take the limit of. We need this handle. It makes this process easier. We need this name y, or this handle y, to do that. Natural log of both sides of this equation gives us natural log y on the left, and the natural log of x to the x allows us now to use the exponent law for logarithms and bring this x in the power down as a multiple of natural log. So now I have x times natural log x. Now what I'll do is say, well, let's take the limit as x approaches 0 from the right, and I don't know how that got so messed up, but let me fix it. X approaches 0 from the right. Here we are. Of natural log of y, which is really just this function. So the limit as x approaches 0 of x natural log x. And let's assess this. It will typically be an indeterminate product at first. X goes to 0, well, x is going to 0. If x is going to 0, natural log of x is going to negative infinity. So this is a 0 times infinity case. Again, it doesn't matter if it's positive or negative infinity. It's 0 times something infinite. So that's how I write the intuition. I need to put this into an indeterminate quotient or ratio. So what I'll do now is, on my right-hand side, I'll push that factor of x down underneath natural log x. So that becomes x to the negative 1 in the denominator underneath natural log of x. Again, if I simplify this expression, observe that I get this one back. I'm just manufacturing a quotient here so that I get an indeterminate quotient from this, and I can use L'Hopital's rule. So as x goes to 0, natural log of x goes to infinity. As x goes to negative 1, as x goes to 0, x to the negative 1 goes to infinity. Here's my indeterminate form, infinity over infinity. Again, negative infinity It might as well be infinity in this case. So the derivative of natural log x is x to the negative 1. The derivative of x to the negative 1 is negative x to the negative 2. Now, limit as x goes to, so I can continue working here. I've got a minus sign that'll come out outside of that denominator. I'll flip x to the negative 2 to the numerator and x to the negative 1 to the denominator to get this expression. Well, that expression simplifies to x, or negative x. As x goes to 0 from the right, negative x is equal to 0 in the limit. Okay, well, that's good. However, this is not the answer. What is this? This is the limit as x goes to 0 from the right of the natural log of y, not y. We want to know the limit of our function y, not its natural log. But we do have very useful information, even though we don't quite have our answer yet. We know that the limit of as x approaches 0 from the right of natural log of y is 0. We can use the fact that exponential functions and logarithms are continuous on their domains, so we can pass the limit through the exponential function. So this is a little bit of a trick. The limit of my original function, x to the x, we named it y. It's equal to the limit as x approaches 0 of y. Now I just need to get in here the limit as x approaches 0 of the natural log of y somehow. Well, in order to do that, I use the cancellation equation. E to the natural log of y is y. So I substitute y for this expression, because it is y. Now, e is a continuous function, so it allows the limit to pass into its argument. And that's what happens in the next line. E to the limit of it as x approaches 0 from the right of natural log of y. Well, now I can assess this limit, and I already know its value because we've already done the work for that. It's here. This is 0. So e to the 0 is 1. And there's our overall answer to that. Okay? Here's the upshot. If you use this method, y equals the function, natural log of both sides, find the limit as x approaches whatever of natural log of y, which is our function with its logarithm introduced. However you evaluate the limit, a couple rounds of L'Hopital, some manipulation, whatever you get to it, you end up here. When you're done, you could just say e to this number is my answer. And that's the easy way out. Always e to that power. Okay, so second example here is another version of this. Let's see, x is approaching infinity in this case. We're taking that limit, and we have 1 plus 2 over x, and outside to the power of 3x. Now, this is an x in the exponent and an x function of x in the base. This is neither an exponential function nor a power function because we have x's in the base and in the exponent. As x goes to infinity, 2 over x goes to 0. 1 plus something going to 0 is approaching 1. 3 times x as x goes to infinity. X is approaching infinity. This has the intuitive form 1 to the power of infinity. This is indeterminate. This thing may or may not converge, and it may converge to some real number or may converge to 0 specifically. We have to find out. So we use the same trick. We have an indeterminate exponential function. So we call it y. Take the natural log of both sides. That allows us to bring the exponent down through the third log law. Now, the limit as x approaches infinity of both sides of this, right, will give us something to work with later here. And this is going to be the limit as x approaches infinity of our function here. Well, x is going to infinity, so 3x is going to infinity. X is going to infinity, so 1 plus 2 over x is going to 1. This is 1 plus 0, essentially. Natural log of 1 is 0. So we have infinity times 0. We have an indeterminate product. So let's just factor this 3 out of the situation altogether and push the x into the denominator, right? It appears underneath there as x to the negative 1, or 1 over x. Remember, that's its reciprocal. And now we check, as x goes to infinity, we have natural log of 1 in here, which is going to 0. We have x to the negative 1, which goes to 0 as x goes to infinity. So we have an indeterminate quotient, 0 over 0. Now we can apply L'Hopital's rule. The derivative of this function is 1 over its argument. So that's this expression here. Remember, 2 over x is 2 times x to the negative 1. I've done a quick, clever change in notation there. Maybe not clever, at least quick. And then the derivative of natural log of something is 1 over that something. Well, another way to write 1 over that something is just to take it to the negative 1 power. So this is just a quick way to write it. But remember, this is a chain rule problem. I've taken the derivative of the outer function natural log. I need to multiply it by the derivative of this inner function. Well, this is 1 plus 2x to the negative 1. Its derivative is 0 plus negative 2 times x to the negative 2. So that's negative 2x to the negative 2 for the inner function's derivative. The denominator, x to the negative 1, has derivative negative x to the negative 2. And now we see a cancellation between negative x to the negative 2 and negative 2x to the negative 2. This 2 will remain as a positive 2, and I'll probably push that out there, I did, as a multiple of this 3. So we have a positive 6 out here. Both of these minus signs have canceled with each other. What's left? The only thing left is this expression. Well, 1 plus 2x to the negative 1 is 1 over 1 plus 2x to the negative 1. Okay, so let me say that again. 1 plus 2x to the negative 1 all to the negative 1 is 1 plus 2x is 1 over 1 plus 2x to the negative 1. This is the reciprocal, push it underneath a 1 to write this down this other way. Okay. X is approaching infinity. Well, this is approaching 0. Right? X to the negative 1. 2 times 0 is 0. 1 plus 0 is 1. 1 over 1 is our expression here. We end up with 6 times 1 over 1 plus 0. And this is a 6. Positive 6. It looks like there was a mistake at some point and that was corrected. So this is not our answer. This is the limit as x approaches infinity of the natural log of y. Remember what I said before, we can pop out of this with the shortcut, whatever this is, take e to it, and you've got your answer. Or if you want some practice, repeat these steps on your own and make sure you understand this chain of steps here in the process involved in order to see that the limit of our actual function is e to the 6. Okay, all of that follows from the fact that the exponential function e, or any exponential function with base greater than a greater than 1, we would say a greater than 0 but not equal to 1. The best way to say that is continuous and would adhere to this property as well. So that's it for L'Hopital's rule and all of our indeterminate forms. We had quotients, products, differences, and powers. So each one has its own sort of set of steps. I think the most clear-cut set of steps are these types of problems. I think differences can be a little bit more dynamic, but if you have the difference of two ratios, get a common denominator, that'll probably work out in your favor. If you have a logarithm involved, then use log laws to get a ratio involved. Pass that limit inside the argument of the log because it's continuous. For products were straightforward as well. You pick one or the other function to push into the denominator. And well, most of the time I would say keep it simple. When we pushed natural log of x into the denominator here, it sort of made a mess out of things. Probably it would have made more sense right out of the gate to just go to this step. It's a little cleaner. But if this way doesn't seem to work out, just always remember you can go the other way. Right? Once we have quotients, well, then we're just off and running for L'Hopital's. We can just apply it until we have something that evaluates. Okay, so that's it for section 3.7.